Hello, everybody. Welcome back. For this lesson, we're going to do two of probably one of the two tests that we're going to be doing is going to be one of the most important that we're going to run into for the next several lessons. We're going to talk about absolute convergence first, and then we're going to do the ratio and root tests. The big one this time is going to be the ratio test. So I'm going to do quite a few examples of that, and we'll talk about that in a moment. But before we do that, let's talk about what absolute convergence means. Up to this point, we have determined whether a series was convergent or divergent. And some of the tests that we've run test for both convergent and divergent. Some of them only test for convergence, some of them only test for divergence. And let's talk about absolute convergence. So a series is absolutely convergent if when we take the absolute value. Now what that's going to do is that's going to knock out that -1 to the n. So we don't need to deal with that anymore. That just turns into a 1 because absolute value of each term means that they're all positive. And a series is conditionally convergent if when we have the actual recognition of whether this is convergent or not. If it's convergent, great, it's convergent. However, if we take the absolute value and it's divergent, then we call it conditionally convergent. So what we can do sometimes is we can just take the absolute value and determine, is it convergent or not? And that brings us to this theorem down here. I know I'm skipping here, but I'll get to that. It says that if this is absolutely convergent, meaning we take the absolute value of each term, make them all positive, and determine that it's still convergent, if that happens, then the whole thing is convergent, which is great for us. So let's take a look at some examples here, and then we'll actually do some examples below. Here we have this. This is absolutely convergent because when we take the absolute value, like I said, the -1 now just becomes a 1. And this is convergent by a p-test. And by the theorem, because it's absolutely convergent, the original is also convergent, which again is our ultimate goal. Now this one here, when we take the absolute value, is divergent because it's a harmonic series. However, if we were to run the test that the alternating series test, we would note that b sub n is 1 over n, and that limit goes to 0 and it's decreasing. So it's convergent. This one is convergent. However, this one is divergent. We would say that this one is conditionally convergent. Because with the alternating series test, the original is convergent. When we take the absolute value, it is not. So that is the difference. We talked about the theorem. Let's jump into the examples. So determine whether this is convergent or divergent. Well, what I'm going to do is I'm going to do the comparison test. And I'm going to note that the cosine of n is always going to be between -1 and 1. And that means it's always going to be less than or equal to 1 over n squared. And we know this is convergent because it is a p-series. Well, let's determine if it's absolutely convergent. Okay, so that gives us this. Now, n squared is always going to be positive, so we don't need the absolute value on that. But once again, by the comparison test, absolute value, that is always going to be less than this here. And once again, we know that that is convergent. So we can make a further declaration that our original series is absolutely convergent. Now, later, we're not going to care if it's absolutely convergent or not. We just want to know if it's convergent, and we'll get to that when we get to some of these other tests. All right, let's determine if this is absolutely convergent or conditionally convergent. And here, I'm going to determine, first of all, that by the alternating series test, b sub n is 1 over 5n plus 1. Remember, with the alternating series test, it's always just the positive part of it. We're not dealing with the negative 1 to the n part. And we know that this is decreasing, and that the limit, as n goes to infinity, of 1 over 5n plus 1 is 0. So we can say that negative 1 to the n over 5n plus 1 is convergent. But let's see if it's absolutely convergent. And again, when we take the absolute value here, that turns that into just a 1. Because negative 1 absolute value is 1, and positive 1 absolute value is also 1. So I'm going to do a comparison test. We're going to compare this to 1 over 5n. And we know that this is divergent. This is a harmonic series, or a p series, if we want to view it that way, where the p is 1 or less, and therefore it is divergent. So I'm going to do the limit, and it goes to infinity. And remember, it's going to be that over that. So this is going to become 5n over 5n plus 1, which is 1. So that means that the 1 over 5n, which is what we have here, is a good comparison. And therefore, we can say that this is also divergent. So we have that it's convergent by the alternating series test, but it's divergent when we take the absolute value. So our overall conclusion is our original, again, divergent when we take the absolute value, convergent when we do another test. So we say that this is conditionally convergent. Let's do a few more examples. Now this one, once again, I'm going to just go ahead and take the absolute value at the get-go. And that denominator is always going to be positive when n is bigger than 1. So I'm going to compare this. One over 2 to the n. I'm going to note that absolute sine of n, or 2 to the n, is always going to be, and by the way, we know that this is convergent by the geometric test. Meaning r in this case is 1/2, which is less than 1. And this is always going to be less than 1 over 2 to the n for all of the terms. And because this one converges, we can therefore say that this converges By the way, this is higher mathematics where this is true, this is true, this is true, therefore we can conclude that this other piece is also true. This is absolutely convergent. All right, let's go back to our theorem that if something is absolutely convergent, then the whole series is convergent as well. That brings us to our first and a very important test, one that we're going to use quite a bit in the next several very important lessons. The ratio test. The ratio test says that if we take one term ahead of another and take the absolute value, take that limit, and that limit goes to a specific number that is less than 1, then the overall series is not only absolutely convergent, but it's also convergent by our theorem. If that same limit goes to something bigger than 1, or it goes to infinity, or it won't go to negative infinity because we're taking the absolute value, then we say that it's divergent. Now, here's where it gets interesting in a later lesson. If this limit exactly equals 1, then we can't use the ratio test. We have to use some other test. And what we're going to end up doing is there's going to be specific values of x that will make it equal to 1, and we'll have to run one of the other many tests that we have. Let's go ahead and start with our example here. So a sub n in this case is here. Now, a sub n, so let's write that out. A sub n is, and I'm going to ignore the -1 at the end because the theorem says take the absolute value, so we're just going to ignore that for now. A sub n plus 1 is there. Now, because I'm dividing, I'm going to actually multiply the a sub n by the reciprocal. That's just going to make it a lot easier. So let's do this. It's going to be the n plus 1 to the third over 3 to the n plus 1 times, and it's actually divided by that, so I'm going to multiply that by the reciprocal. And I'm going to go ahead and break that up. And I'm going to note those reduce out very nicely. And not to be forgotten, we have a 1/3 out in front. All right, so now we have this limit. And what I want to do is I want to point out that if I were to FOIL that out, I would end up with an n to the third, and that would be the largest. So this actually ends up being 1/3 times 1, or 1/3. And the point is, that's less than 1. Therefore, this is absolutely convergent. And therefore, convergent. Now, what it converges to, we don't know, and that's okay. We will get to what that means here, not in this lesson, but in another lesson. All right, so let's use the ratio test here. We're going to have to use some crazy algebra skills here. So we're going to do the ratio test. Now, one of the things that we know to use the ratio test is whenever we have a factorial. That's almost always going to guarantee us that we're going to be using that. Now I'm going to multiply that times a sub n, which is this, but the reciprocal. And like I said, we're going to get some crazy algebra skills going on here. I'm going to break that up. Now I'm also going to take this factorial and break it down just a little bit. This is n plus 1 times n factorial times n to the n. All right, so we have a bit going on here. N plus 1 reduces, n factorial reduces. We're going to end up with an interesting limit that we're going to actually use a couple of times in this lesson. So I'm going to take a minute to break that down. And we end up with, now because they're both raised to the n power, I'm going to actually break that up into that. And I'm going to further break that down into this. And I'm going to do a whole separate thing to figure out what that limit goes to. However, I'm going to use this. Now, why would I choose x instead of n? Well, first of all, the limit is going to go in the same direction. And second of all, x is now continuous, which means I can do fun things like derivatives and apply L'Hopital's and blah, blah, blah. So now that I have a continuous function, I'm going to do this. I'm going to rewrite this as e to the ln of the whole thing. Now, again, those cancel out. I'm back to here. And I'm going to do this. And I'm going to further do this. Now, why on earth would I do that? Well, what I'm going to do is I'm going to take the limit. And again, this limit as x goes to infinity is going to go to the same place, but I'm just going to do it to the numerator. I'm going to note that this goes to 0 over 0, which is inconclusive as far as what the limit is. However, this means I can apply L'Hopital's rule. So I'm going to apply L'Hopital's rule to this. That's going to become 1 over 1 plus 1 over x times negative 1 over x squared, because the chain rule, I need derivative there, over that. And we will notice that goes away. This we can deal with. Now I'm going to notice that as x gets really big, that whole piece right there goes to 0. So what's the limit? This is a 1. Now remember, this is just the exponent. Therefore, the limit as x goes to infinity and later n goes to infinity of 1 plus 1 over x to the x is exactly equal to e to the 1 power, or just e. Keeping that in mind, this is exactly the same scenario. So this limit right here is going to go to E. Now E, if you recall, is a number that is, pardon me, E in this case, again, this is the exact same scenario that we just proved. It's a number that is bigger than 1. In fact, it's 2.7 and change. And according to the theorem, if the limit is bigger than 1, then the series overall is divergent. Now we will use this limit again for another problem in a few minutes. Let's do a bunch more examples. Again, the -1 becomes irrelevant. So we're going to use the ratio test. With the limit as n goes to infinity of absolute value 3 to the n plus 1 over 2 to the n plus 1, n plus 1 to the third, times the reciprocal of that, because we're actually dividing it. Now, I'm going to break these up. Also down here. Now, there's a lot going on here, but we're going to manage it. 3 to the n is gone. 2 to the n is gone. Now I am left with a 3 and a 2. And an n to the third over n plus 1 to the third. Now, once again, what we have is, if I were to FOIL that out, we would have n to the third over n to the third. This whole piece goes to a 1. Which means this limit is 3/2. And unfortunately, 3/2 is bigger than 1. Therefore, the whole series is divergent. All right, let's try example 7. This is a special one. We'll come back to that one in another video. This actually has some meaning. If you were to plug in n equals 1 plus n equals 2 plus n equals 3 and so on into the factorial there and add them up, maybe the first 10 things, you'll recognize where that number is going. But let's do the ratio test. And again, whenever we have a factorial, we're almost always going to do the ratio test. In fact, I can't think of a suggestion when it's not. So this is going to be n factorial over n plus 1 factorial. Remember, it should be 1 over n plus 1 factorial over 1 over n factorial, and everything gets flipped around, and we end up there. Now, this is a really important one, as I mentioned, and something really cool is going to happen here. That limit goes to 0. And what makes that cool is 0 is always going to be less than 1. In fact, that's as less than 1 as you can go. And even if I have numbers out here, like I had 2/3 before, or 3/2, pardon me, out in front, doesn't matter. If that limit goes to 0, the whole thing is going to be less than 1 always. So our conclusion that this is absolutely convergent, therefore convergent. By theorem, right? So the first theorem says that if this is less than 1, then it's going to be absolutely convergent. And the other theorem that we had says if it's absolutely convergent, then it's convergent. All right, we've got a couple more we're going to do. So let's do the ratio test. Remember the n plus 1 is going to be at the top. Now, when I plug in n plus 1 there, I'm going to have, let me kind of show you what I mean. Some scratch paper. So if I have a sub n is 4 to the 2n plus 1. A sub n plus 1, which I'm going to need here, becomes 4 to the 2 times n plus 1 plus 1. Now that gets a little bit messy. Notice it goes from 1 to 3 when I increment n by 1, because we have to do distributive property and combine terms and stuff. So this becomes to the 2n plus 3 times the reciprocal of that. That is messy, but that's okay. So let's break this down a little bit. And when I break it up like we did before, do you see I'm going to get a 4 to the 2n that's going to reduce out, and I'm going to get a 4 to the third and a 4 to the first power here. Also the 10 to the n goes away, and I'm left with a 10. So let's sort all of that out. Up top, I'm going to have a 10 and a 4. 10 and a 4. In the bottom, I'm going to have a 4 to the third power. And I'm going to be left with n plus 1 over n plus 2. Now again, the plus 1 means that I get a 10 that's going to come out. The plus 1 means I'm going to get a 4 that comes out. Here, the plus 3 means I'm going to get a 4 to the third. And I'm going to notice that I can reduce a 4 out of that. This limit goes to 1. Degrees are the same, so that whole limit there goes to 1. And that reduces with that. This limit becomes 10 over 16, which we can reduce to 5 over 8. Whew, that one's a little dense. So the whole point is 5/8 is less than 1. That's the whole key there. So this is absolutely convergent, and therefore convergent. All right. Next up, our last ratio test one for this lesson is here. Now, a couple of things we can do. Because it's absolute value, that negative goes away. Because when we're taking the absolute value, it doesn't matter. So let's do the ratio test again. The n plus 1 terms, that's going to be n plus 1, pi to the n plus 1 over 3. Now, n plus 1 minus 1 is just going to be 3 to the n times the reciprocal of this. Now, what we're going to notice here is that the 3 to the n is gone, and the pi to the n is also gone. Now, that means that I'm left with a pi, let's pull that out, times 3 to the negative 1 power is what that means there. Then we have absolute value of n plus 1 over n. Once again, this goes to 1 because the degrees are the same. And because it's a negative 1 power, we end up with pi over 3. Now pi is 3.14159 and so on. Some of you may know many more digits than I know. Point is, it's bigger than 3. The point is, that makes the whole thing bigger than 1. Therefore, this is divergent, because that limit is bigger than 1. All right, we are to the last page actually. And we're going to do another test. This one is not used as much, but it has its utility. This is called the root test. Now, it's the same rules as the ratio test. However, we are now taking the nth root of the absolute value of a sub n. And once again, if that limit is less than 1, it's absolutely convergent, therefore convergent. If that limit goes to something bigger than 1 or infinity, it's divergent. And another big thing here is if it's equal to 1, that means we can't use, I see there's a typo here, the root test, meaning we'll have to use a different test. And usually if the root test fails, meaning we can't use it, it's inconclusive, that means the ratio test also is going to become inconclusive. Now we're going to want to use the root test when we have things raised to the n power, because then they're going to cancel themselves out. So let's just do this. So we're going to use the root test. So we're going to have the nth root of 2 to the n plus 3 over 3n plus 2, the nth power. Now, what's nice is those completely cancel out. So we end up with the limit of, and of course this is absolute value. In this particular case, the absolute value is irrelevant. Because the lead coefficients are 1, both 1, they're the same. The degrees are the same, I should say. The lead coefficients take over. And there is our limit. And the big thing is this limit less than 1, bigger than 1? This is less than 1. Therefore, our overall series is absolutely convergent and therefore convergent, which is the goal. So later we'll learn we want things to be convergent. It makes things much nicer. Now you'll note this is to the n power. That's screaming out, let's use the root test. Again, nth root of and of course this is supposed to be absolute value, which in this particular case becomes irrelevant. The nth root and the nth power cancel out completely. And the degrees are the same, second degree. So the lead coefficients, the 1 over the 2, take over. So this limit goes to 1/2. which of course is less than 1. So our conclusion is that this is absolutely convergent and therefore convergent. Now, for this one, what's going to happen is this numerator, because we're doing absolute value, just becomes a 1. So I'm just going to ignore the -1 and the n power and all that kind of stuff. It just becomes a 1. And the good news is 1 to any power is always just 1. So we end up with this here when we do the root. The nth root of 1 over n of n, the nth power, absolute value. Now, 1 to the n power, 1 over n power, I guess, is just always going to be a 1. This one, the exponents cancel out completely. We just end up with ln of n. Now you'll note that ln of n, as n goes to infinity, the whole thing goes to infinity. And as the denominator gets large, the whole thing goes to 0, which is clearly less than 1. Therefore, this is absolutely convergent, which means it is convergent by theorem. All right, this last part is we're going to use the root test. You can see the n squared there. And that nth root is going to get rid of one of those, not both of them, but the whole one of them. So this limit, as n goes to infinity, absolute value of 1 plus 1 over n to the n power. Now the absolute values are irrelevant in this case, this whole thing, because n is going off to positive infinity. We're going to get positive there. And I want us to recall, I have already proven that this limit goes to e. I told you we were going to come back to that at some point. So this overall limit exactly equals e. And what can we conclude from that? Well, e is 2.7 and change. So e is definitely bigger than 1. And therefore, our overall series here is divergent. Again, we are going to use the ratio test, definitely coming up here. Yep, that is absolute convergence and conditional convergence, the root test, and the ratio test. Thanks.